Somewhere in the freezing darkness between the stars, something is heading toward our solar system. It does not belong here. It was not born here. It formed under a different sun, in a different solar system, billions of years ago, and it has been drifting through interstellar space ever since. Frozen, pristine, completely untouched by our sun's heat or chemistry. And when it arrives, for the first time in human history, we will not just watch it pass. We will intercept it. Europe's Comet Interceptor mission is unlike anything ever attempted in the history of space exploration. Not because of where it is going, but because of the fact that when it launches, nobody knows what it is going to intercept. The target does not exist yet. It has not been discovered. It is out there somewhere in the dark, and we are launching a spacecraft to ambush it before we even know its name. This is the story of the most daring cosmic stakeout ever planned. A spacecraft built to intercept a visitor from another star. And the science it will return could answer one of the oldest questions in human history. Are the ingredients for life scattered across the galaxy? In 2028, a rocket will lift off from Kourou in French Guiana, carrying 2 spacecraft into orbit. One of them is Ariel, ESA's Exoplanet Atmosphere Telescope. The other is Comet Interceptor, hitching a ride as a co-passenger. But unlike Ariel, Comet Interceptor will not immediately begin its mission. It will park. Approximately 1.5 million kilometers behind Earth as viewed from the Sun sits a location called the Sun-Earth Lagrange Point 2, or L2. At this precise point in space, the gravitational pull of the Sun and Earth balance each other perfectly. A spacecraft placed here requires almost no fuel to maintain its position. It simply hovers, stable, patient, waiting. This is where Comet Interceptor will sit. For months, possibly years. Doing nothing but waiting for a phone call from Earth telling it a target has been found. This approach is completely new in the history of space exploration. Every mission ever launched before this one had a known destination. Engineers calculated the trajectory, aimed the spacecraft, and sent it on its way. Comet Interceptor inverts that entire model. It launches first. It finds its target later. It is the first spacecraft in history designed to intercept something that has not been discovered yet. The reason for this radical approach comes down to a problem that has frustrated astronomers for decades. Pristine comets, objects making their first ever approach to our sun, are only discovered months or at most a few years before they reach their closest point. By the time we see them, there is not enough time to design a mission, build a spacecraft, launch it, and intercept the comet before it swings past and disappears back into the outer solar system forever. By parking Comet Interceptor at L2 in advance, ESA eliminates the build time from the equation. The spacecraft is already in space, already fueled, already pointed outward. The moment a suitable target is identified, it can begin its transfer trajectory immediately. The waiting is the strategy. To understand what Comet Interceptor is hunting, you need to understand the difference between a comet from our own solar system and something genuinely alien. Most comets originate from the Oort cloud, a vast spherical shell of icy debris surrounding our solar system at distances of up to 100,000 astronomical units from the Sun. These objects formed from the same material as our planets billions of years ago. They carry the chemical signature of our solar neighborhood. When they fall inward toward the Sun, they heat up, release gases, and develop the glowing tails we see from Earth. Every comet humanity has ever studied up close came from this local reservoir. Even the most scientifically valuable ones, like Comet Halley visited by the Giotto mission in 1986, or Comet 67P studied so intimately by the Rosetta mission, had already made multiple passes around the Sun before we reached them. Each pass altered their chemistry, heated their surfaces, evaporated their most volatile compounds. By the time we got to them, they were already changed. Comet Interceptor is targeting something different, something that has never felt our sun's heat at all. In 2017, astronomers detected an object passing through our solar system on a trajectory that could not have originated here. Its path through space was too fast, too steeply inclined to the orbital plane of our planets. It was moving on a hyperbolic trajectory, meaning it came from outside our solar system entirely. They named it Oumuamua. It passed through our entire solar system before anyone realized what it was. By the time telescopes were pointed at it, it was already leaving. We had weeks to observe something that had traveled for billions of years to reach us. We watched it disappear and learned almost nothing definitive about what it actually was. If a target like Oumuamua were discovered today, with Comet Interceptor already waiting at L2, we would have a chance to actually reach it, to fly alongside it, to sample its gas envelope, map its nucleus, and read the chemical story written in its frozen surface. That story would be unlike anything we have ever read before, because the chemistry of an interstellar visitor reflects the solar system it came from, not ours. Its isotope ratios, its molecular composition, its dust particles, all of it formed under a different star, in conditions we have never directly sampled. It would be the first physical contact humanity has ever made with matter from another solar system. When the target is finally identified and Comet Interceptor begins its transfer trajectory, it will not arrive as a single spacecraft. It will split into three. The mission consists of a primary mothership and two smaller sub-probes. As the fleet approaches the target comet, the probes separate and fan out into different positions around the object. The mothership and both probes will fly past the comet simultaneously, each from a different angle, at a different distance, with different instruments, building a complete three-dimensional portrait of something humanity has never examined before. This multi-spacecraft approach solves a fundamental problem with comet flybys. A single spacecraft sees the comet from one perspective at one moment in time. Dust, gas, and plasma jets erupting from the nucleus change from second to second. A 3D view captured simultaneously from three different positions gives scientists something far more powerful than three separate flybys could ever provide: a complete snapshot of the comet's entire environment at a single instant. The primary spacecraft carries the longest range instruments, cameras to map the nucleus from a safe distance, spectrometers to analyze the chemical composition of the gas coma surrounding the comet, and magnetometers to measure its interaction with the solar wind. One sub-probe will fly closer, into the inner coma where the gas density is higher and the chemistry is richer. The second sub-probe will pass closest of all, sampling the immediate environment around the nucleus in the highest possible detail. Together, the three spacecraft will build a picture no single probe could ever assemble. The shape of the nucleus, the temperature of its surface, the exact molecular composition of the gas it releases as it warms for the first time, the size and composition of the dust particles streaming away from it. And if the target is an interstellar visitor, every single one of those measurements will carry information that has never existed in any human database before. The scientific case for Comet Interceptor rests on a simple but profound idea. Chemistry is a fingerprint. Every star system that has ever existed left its chemical signature in the objects it formed. The ratio of different isotopes, variants of the same element with different numbers of neutrons, varies depending on the conditions present when a solar system formed. The specific molecules preserved in the ice of a comet reflect the molecular cloud the star was born from. The dust particles embedded in its surface carry the direct physical products of nucleosynthesis, the stellar processes that created the atoms themselves. Every comet from our own Oort cloud carries our solar system's fingerprint. We know what that fingerprint looks like. We have studied it across dozens of missions over decades. An interstellar comet carries a different fingerprint entirely. The fingerprint of another star, another solar system, another history billions of years long that we have never had access to before. Specifically, scientists want to measure the deuterium to hydrogen ratio in the comet's water ice. This ratio is different in different parts of the galaxy depending on how and where the water formed. Comparing it to the ratio in our own solar system's comets and in Earth's oceans could tell us something profound about how water, and potentially life, gets distributed across the galaxy. They want to measure the ratio of left-handed to right-handed amino acid molecules, if any are present. On Earth, life uses almost exclusively left-handed amino acids, an asymmetry whose origin remains one of the deepest unsolved problems in biology. If an interstellar comet carries the same preference, it suggests this asymmetry is not a local accident, but a universal property of chemistry under certain conditions. They want to map the dust particles, their size, their mineralogy, their structure, and compare them directly to the dust found in our own solar system's comets. If the dust from another solar system looks the same as ours, it tells us planetary formation is a universal process producing similar building blocks everywhere. If it looks different, It tells us there are multiple pathways to building planets, and potentially multiple pathways to building the conditions for life. Every molecule Comet Interceptor samples is a word in a story written by a star we will never visit. Comet Interceptor cannot do its job alone. The spacecraft can wait at L2 indefinitely, but it needs eyes on the sky to tell it when a target has arrived. Those eyes belong to one of the most powerful astronomical instruments ever built, the Vera C. Rubin Observatory in Chile. The Rubin Observatory is designed to survey the entire visible southern sky every few nights, detecting objects as faint as anything ever systematically cataloged. It will find asteroids, comets, supernovae, and transient events at a rate that dwarfs every previous sky survey combined. And crucially, it will find long-period comets and interstellar objects years earlier than previous surveys could, giving Comet Interceptor the advance warning it needs to actually reach its target before it passes. The combination of these two instruments, one on the ground scanning the sky, one in space ready to launch at a moment's notice, represents something genuinely new in the history of science. We are no longer simply watching the universe through telescopes. We are preparing to physically reach out and touch pieces of it. That is the shift this mission represents. Every mission before Comet Interceptor studied the universe from a distance. Telescopes collected light that had traveled billions of years to reach us. Spectrometers analyzed that light and deduced chemical compositions from the wavelengths it carried. We learned an enormous amount, but we were always reading the universe's story secondhand, through the medium of light rather than through direct contact with the matter itself. Comet Interceptor will reach out and physically encounter material from outside our solar system for the first time. Not light that originated elsewhere. Matter. Actual atoms that formed around another star, in another solar system, in another part of the galaxy, and flew across interstellar space to arrive here. In our neighborhood, within reach of a spacecraft, we had the foresight to park and wait. Here is the thought that should stay with you long after this video ends. Our solar system is not a closed system. It is not an island. For billions of years, material has been flowing between star systems across the galaxy. Comets and asteroids ejected by gravitational interactions, drifting through interstellar space, occasionally passing through other solar systems, occasionally being captured, occasionally being observed by civilizations advanced enough to look. Oumuamua was not a unique event. It was the first one we noticed. Statistical models suggest interstellar objects pass through our solar system regularly. We simply lack the instruments to detect most of them until very recently. What this means is that our solar system has been in contact with the rest of the galaxy for its entire existence. Material from other star systems has passed through here before. Some of it may have been incorporated into comets, asteroids, even planets. The atoms in your body were forged in stars that died before our sun was born, but some of them may have traveled through other solar systems on their way here. We are not as isolated as we thought. Comet Interceptor will launch into this understanding and return something we have never had before, a direct physical sample of the interstellar exchange that has been happening silently around us for billions of years. It will not find life. It will not find alien technology, but it may find something in some ways more profound. Evidence that the chemistry of life is not unique to our solar neighborhood, that the same building blocks, the same molecular precursors, the same asymmetries that make biology possible here, are scattered across the galaxy in the frozen hearts of wandering